Welcome to our deep dive. Today, we're tackling Hilbert's program, and I know you're coming at this from a philosopher's perspective, so we'll definitely keep that in mind as we go. We're mainly using Richard Zach's entry in the Stanford Encyclopedia of Philosophy for this one.
Oh, excellent choice. It's really a treasure trove for this kind of deep dive. Hilbert's program. It just brings up so many fundamental questions about math, logic, knowledge, all the good stuff.
Exactly. Okay, so picture this. It's the early 1900s. And mathematicians are having a bit of a crisis. Paradoxes are popping up in set theory, and it's making people question, like, the very foundation of math, you
Well,
know?
absolutely. Talk about a time of intellectual upheaval, right?
Mm.
And right in the middle of all this, you have David Hilbert, one of the giants of mathematics. He steps up with this incredibly bold idea, Hilbert's program.
So for our philosopher friend listening in, can you break down what this Hilbert's program was all about?
Well, Hilbert, he wanted to build this absolutely unshakable foundation for all of mathematics. Imagine like a perfect system where no contradictions could ever sneak in. That was his dream.
It almost sounds like he was trying to write a constitution for math, a set of rules to guarantee that all mathematical reasoning is consistent and complete.
That's a fantastic way to put it. He truly believed that you could boil all of mathematics down to this like formal system, a game with super strict rules. The goal, you see, was to find a set of axioms, starting points, and from there you could derive every single mathematical truth using pure logical deduction. No room for error.
But why was this so crucial to him? Was it just about fixing these paradoxes in set theory, or were there some deeper philosophical reasons driving him?
Well, the paradoxes were definitely a big motivator, no doubt. They were causing a lot of anxiety among mathematicians at the time. But you also have to consider the wider philosophical landscape. This was a period where movements like logicism and intuitionism were really challenging traditional views of math.
Right, like intuitionism. They rejected some of the core ideas of classical mathematics, especially when it came to things like infinite sets.
Exactly. And Hilbert saw his program as a way to defend that traditional view of math, that classical approach against these new challenges. He was convinced that mathematics was, at its core, a logical system. And his program, he believed, would prove its consistency and completeness once and for all.
So it wasn't just a matter of patching up some holes. He was fighting for a whole philosophical vision of mathematics.
Absolutely. And a big part of that vision, one that's particularly fascinating from a philosophical standpoint, is this idea of the finitary standpoint.
Okay, now we're getting to the good stuff. Break that down for us. What did Hilbert mean by finitary?
So for Hilbert, the finitary standpoint was all about rock-solid certainty in math. It meant limiting our thinking to objects and operations that are totally concrete, that you can grasp intuitively. Like the basic stuff of arithmetic, counting, adding, subtracting. These were perfect examples of finitary operations for Hilbert.
So we're talking about dealing with mathematical objects that are tangible in a sense.
Precisely. And the beauty of these finitary operations, according to Hilbert, was that they were immune to those pesky paradoxes plaguing set theory and other areas. He believed that by grounding all of mathematics in this finitary standpoint, you could completely eliminate the possibility of contradictions.
But how do you get from these basic, tangible operations to the more complex world of higher mathematics? That seems like a pretty big jump.
And that's where formalism comes in. Formalism is this philosophical idea that sees math as a kind of formal game, a manipulation of symbols according to a very precise set of rules. Hilbert's program aimed to show that even the most complex mathematical ideas could be broken down into these finitary, rule-governed operations.
So you're saying that even the most elaborate mathematical structure is built on these simple foundational blocks.
Exactly. And if you can prove the consistency of those basic building blocks, then, according to Hilbert, you've proven the consistency of the whole mathematical structure.
But did he think that this meant math was essentially meaningless? Just a game of symbols with no connection to the real world?
Now that's a great question. And it gets right to the heart of the philosophical debate around formalism. You see, while some critics accused Hilbert of stripping math of its meaning, he actually drew a distinction between the formal system itself and how we interpret it. He argued that, yes, the formal system might be seen as kind of meaningless in itself, but we can still use it to model and represent things in the real world.
It's like the relationship between a map and the territory it represents. The map itself is just lines and symbols, but it can still be incredibly useful for navigating the real world.
That's a perfect analogy. Hilbert's point was that even if we see math as this formal system, a kind of game, it can still be profoundly connected to reality and help us understand the universe.
Okay, so we've got this Hilbert's program trying to build a super solid foundation for math. using this finitary approach. It's like seeing math as a formal game, right? But I feel like there's got to be more to the story.
Oh, there definitely is. You see, Hilbert's grand plan, as amazing as it was, ran smack into a big fat obstacle, Gödel's incompleteness theorems.
Ah, yes, those famous theorems. Even people who aren't deep into math have probably heard of them. Can you explain, like, what Gödel actually proved and why it caused such a huge stir, especially for our philosopher friend listening?
Well, Gödel's theorems were like one of those unexpected twists in a movie that makes you question everything. They revealed that even the most carefully built formal systems have some built-in limitations.
Okay, that's pretty intriguing. Can you maybe unpack the first theorem for us a bit?
Sure thing. So Gödel's first incompleteness theorem says basically that in any formal system of mathematics that's strong enough, there will always be some true statements that you can't actually prove within that system.
Wait a minute. So there are mathematical truths out there that we might, understand intuitively, but can never actually prove using the rules of the system? That's kind of mind-blowing.
It is, isn't it? And it really shook things up because it suggested that a complete and consistent axiomatization of all of mathematics, which was Hilbert's big goal, might be impossible. There will always be some missing pieces that you can't prove within the system, even though they might be true in a bigger sense.
Like having a puzzle with pieces that clearly belong, but they just won't fit in the frame.
Exactly. A perfect analogy. Now, if that first theorem was enough of a head scratcher, Gödel's second incompleteness theorem delivers an even bigger blow.
Uh-oh. I'm a little scared to ask, but go ahead. What's the second one about?
Well, the second theorem says that a consistent formal system, if it's powerful enough, can't actually prove its own consistency. Basically, it might be totally free of contradictions, but it can't prove that fact within itself.
Wow, that's a real paradox. If a system is consistent but can't prove its own consistency, doesn't that create some kind of crazy logical loop?
You got it. And this was a big problem for Hilbert's program because he wanted to use those super concrete finitary methods to prove the consistency of his system. But if the system itself can't prove its own consistency, even if it is consistent, then those finitary methods hit a wall.
It's like trying to fix a really complicated machine with just a tiny screwdriver. The screwdriver might be useful, but it's not going to get the whole job done.
Precisely. Gödel's theorems show that there's a fundamental limit to what you can do with formal systems alone. It's not that Hilbert was wrong or his methods were bad. It's more like the very nature of mathematical truth is just way more slippery and complex than maybe he originally thought.
These theorems must have been like an earthquake for mathematicians, like realizing that the universe is weirder than we can even imagine.
Absolutely. So Gödel's theorems forced everyone to rethink Hilbert's program. It wasn't completely abandoned, but people realized they needed to adjust the plan. So mathematicians and philosophers started exploring what they called relativized versions of the program. They accepted the limitations of formal systems, but kept looking for ways to ground mathematical knowledge in more basic systems.
So they didn't give up on finding a solid foundation. They just changed their strategy.
Yeah.
What were some of the new directions they took?
Well, there were a few really interesting paths that emerged. One was called ordinal analysis. It's all about figuring out how strong different mathematical theories are based on how much they rely on inductive reasoning. It's basically a way of categorizing and comparing different systems.
So instead of building one giant, all-encompassing mathematical structure, they started focusing on understanding the strengths and weaknesses of different approaches.
Exactly. Another direction was proof-theoretic reduction. This is all about showing that certain parts of math can be reduced to simpler systems, but without losing any essential truths, like finding a way to simplify the blueprints of a complex building without messing with its structure.
So instead of trying to build the whole thing from scratch, they started looking at ways to solidify individual parts of the structure, make sure everything is sound and fits together.
Exactly. And then there's reverse mathematics, which is a really cool area. It tries to figure out the absolute minimum assumptions you need to prove different mathematical theorems, like asking, what's the simplest foundation this mathematical idea can stand on?
So while Gödel's theorems threw a wrench into Hilbert's original vision, they also opened up a whole new world of exploration into the foundations of math.
Absolutely. And that's really the amazing legacy of Hilbert's program. It keeps inspiring new research and philosophical debate, even in these modified forms. The quest to understand the foundations of math, even if it's more nuanced and complex than Hilbert first thought, is still a really exciting intellectual adventure.
Wow, we've really been through the ringer with this Hilbert's program, huh?
Oh, yeah, though.
All those big dreams, the philosophy behind it, and then Bam, those incompleteness theorems.
It's been quite a journey, that's for sure. But I guess the question now is, where does all this leave us? Like, what can our philosopher friend take away from all this? What's the lasting impact of Hilbert's program, even if things didn't quite go according to plan?
Right. Like, I mean, Gödel showed us that maybe we can't have that absolute certainty in math that Hilbert was hoping for. But does that mean the whole program was a bust?
Oh, not at all. One of the biggest things to come out of all this is that Hilbert's program, even with its hiccups, it completely changed how we think about mathematics. Mathematicians and philosophers, they had to start wrestling with some really big questions. Like, what is proof, really? How does logic connect to truth? And what are the limits of these formal systems we build?
So even if we can't have perfect certainty, the search for it was still super valuable.
Exactly. Hilbert's program basically launched all these new areas of research like proof theory and the study of formal systems. And that had a huge impact, not just on math, but on computer science, logic, philosophy. It's like setting out to find a new island and discovering a whole new continent by accident.
I love that. It really shows how powerful intellectual curiosity can be.
Hmm.
But I got to admit, I'm still kind of stuck on Gödel's theorems. The idea that there might be true mathematical statements out there that we can never prove, it's a bit humbling and honestly a little scary.
I know what you mean. It makes you wonder, right? But in a way, it's also kind of awesome. It tells us that mathematics isn't just this closed box of rules and formulas. It's this living, breathing thing full of mystery and surprises. It's a place where intuition and creativity still matter.
Yeah, so it's not just about getting the right answers. It's about asking the right questions, pushing the limits of what we know and how we know it.
Exactly. And thinking about all this, I have a final thought for our philosopher friend listening. We've talked about Hilbert's idea of mathematics as a formal game, but what if we look at that analogy in a slightly different way? Instead of a game with fixed rules, imagine mathematics as a game where the rules themselves are always changing as we learn more. A game that keeps evolving.
Oh, I like that. It's like saying that mathematics isn't this static, finished thing. It's alive and constantly growing.
Right, and maybe that's one of the things that makes math so endlessly fascinating. We might never reach that absolute certainty Hilbert was looking for, but the search for the foundations of mathematics will always be this exciting journey full of unexpected twists and turns and amazing discoveries.
Well said. And to our listener, thanks for joining us on this deep dive into Hilbert's program. We hope you've enjoyed exploring this incredible world and that you've come away with a new appreciation for the beauty, the complexity, and the enduring mystery of mathematics.
Until next time.